The next topic we're going to be looking at is work and energy, and you could make an argument it's the single most important topic I'll teach you. In fact, we're going to learn something called the law of conservation of energy, which in some ways is more important than the law of conservation of momentum. We'll get to that in a couple of days. The law of conservation of energy is my fallback, my go-to when someone says to me, "Hey, Calvin, you teach physics." Well, yeah, I do. Would it be possible for Superman to blah, 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 blah? Hey, I saw Marvel Comics. Would it be possible for the Hulk to blah, 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 blah? Hey, would it be possible to build a machine that would blah, blah? Almost always when I say to them, no, the explanation involves the law of conservation of energy. It's a fundamental universal law. It's also partly what explains why all of you will die someday, and all of you will die someday. The death rate is still 1-to-1. Preview of coming attractions. In about 150 years, most of your atoms will be in other people's bodies. Just letting you know. Lesson 1, the first thing we have to define is work. In physics, work has a specific meaning. Work is not getting tired. I see people say, oh, I'm working hard. Okay, work is not building up a sweat. Work is not getting tired. In fact, in physics, work is done on an object. You do work on an object. And if you're doing work on an object, two things must happen. First thing, you must apply a force to the object. And the second thing, the object must move through a distance in the direction of a force, of the force. Work is a scalar. Symbol capital W for work. And it's calculated by force times distance. But the distance has to be in the same direction as the force. It can be in the opposite direction, we'll call that negative, but it must be in the same line as the force. What are the units for work? Well, what are the units for force? Hello? Newtons. What are the units for distance? So technically it's a Newton meter, but we've long since given that a name. We've said that work is measured in joules, symbol capital J, named after a scientist whose last name was Leroy. No, Joules. Okay. Another key concept, this equation here only works if the force is a constant force. If the force is changing, we're going to need to fudge things. To be honest, if the force is changing, you need calculus, but I can do some limited changing force ones with a bit of care. Bring that question into the recording, Braden. What was your question? So I just did my piggyback illustration to show that when you're piggybacking someone and walking with them, because gravity is down but the walking is horizontal, you're doing no work on that person. Go ahead.
Why do you feel tired?
Can you save that for a couple of days and I'll be able to give you a complete and a good explanation, okay? You feel tired because you are using up energy. There is a way that you're using up energy and it is actually in the direction of motion, but I can't get you there yet. Great question, though. I was hoping somebody would ask. So, a basic, though, this explains why, if nothing else, it tires you out to lift things. How much work does it take to lift a 12-kilogram mass, you know what, underline the word lift, from the ground to a height of 9.5 meters? If you lift, you're moving it in this direction, and the force is in this direction, you will be doing work on this object, on this mass. So we're going to start out by saying, well, work is force times distance. But now we can be more specific. When you lift something, which force are you doing work against? Gravity. So if you want to put a little tiny g next to the F. Who remembers what was FG? We always broke that down into 2 letters all the time. Get the obvious one is what I always said. What was it? MG? times the vertical distance. By the way, look up. Because it's a vertical distance, you may see it written as mg. In fact, you will see it often written as mgh for height, just to make sure that we're cluing in, keep the distance vertical. So it's going to be 12 times 9.8 times 9.5. You have done work on this object. How much work? That much. That much. 1,117.2, 1,117.2. You know what? I'll call it 1.12 times 10 to the third joules. I'll go to 3 sig figs. That one right there will become a 2. Is that a lot? 12 kilograms, about 25 pounds. It's about that lead weight that I have sitting over there, if any of you have handled it. 9.5 meters, about 3 stories. All of you could do it. Some of you might be a little tired when you got to the top of the 3rd stair, but all of you could do it. Going back to Braden's question, one of the things that influences how tired you get isn't how much work, it's how fast you do the work. This is why you get, have you ever run a set of stairs for Mr. Goulet in a practice? Okay, running the stairs is more tiring than walking the stairs, even though you're actually raising the same mass, your mass to the same height, same stairs. One of the things we'll talk about is the rate at which you do work. We'll have to define that. Hey, Braden, stand up. I said Cody, but we'll use Braden. Push against the wall as hard as you can. For 12 seconds. Push. 1, 2, come on, push! 5, 6, come on! 7. Okay, you can stop. This again goes back to Braden's question. Now, he was getting tired, but did the wall move? Did you do any work on the wall? Did the wall move? Was there any distance? Did the wall move? No. Was there any distance? So did you do any work on the wall? No. Okay. Here, it's going to be work equals force times 0. Didn't move. I know you got tired, but it's okay. It's not work. Another way to think about work, Nevada, is as a transfer of energy, and we'll start talking about that too. But really, the reason Braden did no work on the wall is he didn't transfer any energy to the wall. The wall neither gained energy. The reason that James did no work on Cam when he piggybacked him was he never transferred any energy to Cam. Cam never gained nor lost energy. Pushing a box along the floor requires a steady force of 22.5 newtons. A constant force, as it were. Oh, you know what? I think that also means that friction and the applied force are the same, because that's how you would get a constant force, a constant acceleration. Little review, right? How much work have you done if you push it for 13.6 meters? Okay. The work is going to be, in this case, the applied force times distance. You can imagine, here's the floor, here's the box. The force is this way. The distance is this way. The key idea, Tyler, are the force and the distance, if you look at my little picture there, in the same direction? Yeah. Are the force? Yeah, then there's work. Okay? It's going to be 22.5 times 13.6. $306. 306 what? Joules. Let's go bike riding. Dylan pedals his bike up a 19-meter high hill. The hill is 91.4 meters long. The combined mass of the rider is 65 kilograms. The bike requires a steady force to continue up the hill. You know what? I forgot to include the steady force here, didn't I, Mr. Dewick? Give me 1 second. Let me pause the video. I knew I'd forgotten something. If the hill, you know what? I realize why I didn't give you the force. I don't need the force. I didn't need to give it to you. So here's what it says. If the hill is at a 12-degree angle, how much work does Dylan do? If I use this number here along the hill, then I would need exactly the pedaling force up the hill. Did they tell me the pedaling force up the hill? No. But wait a minute. When you pedal up a hill, which force are you doing work against? The hill, huh? Gravity. Gravity. Which way does gravity act? Right? Is there a distance in that direction by any chance in the question? There is? I don't need to know how hard you pedaled. I can tell you how much work you did. The work is going to be the force of gravity times the height of the hill. It's going to be mgh. Cam, did they give me the mass of the bike rider? What? What's g? Mr. Duick, negative or positive? Work's a scalar. So am I going to put the negative of the... Nope. Okay. What's h? How much energy would it take to get to the top of the hill? How much work would you need to do? This much. $12,103 joules. That's one of the lovely things about work. Work does not care about the path that you took to get to a location. All it cares about is the difference between where you started and where you ended. In this case, since the force is vertical, all it cares about, Taylor, is the difference in vertical distance, the height. In fact, how much work would it take for Dylan to ride to the top of this hill? I don't care about the fact that it's all curvy. All I care about is if you're riding up a hill, which force are you doing work against? It's going to be that. It's going to be mgh. Cam, the mass was 65. 9.8, don't need the negative, it's a scalar. What's h this time? 24. Now you might say, hey, wait, Mr. Duick, but he's going downhill and then back uphill. Yeah, but you know what? Any energy he gains going downhill, he loses going up. It all balances out. Work is a lovely scalar. It's fine. In fact, this would even work if it was a staircase. Now you can't ride a bike up a staircase, but when you walk up the stairs, for example, I treat that mathematically just like you climbed straight up a ladder. You did the same amount of work. Still haven't given you a good explanation for tiredness yet, but we'll get there. Cam says, I'm an expert on tiredness in the morning. Yeah, whatever. 15,288? I'll go 15,300. Really, I should be going to 2 or 3 sig figs. Really, 2 sig figs. Work measured in units? Joules, okay? So here's our new unit for the day. By the way, before you turn the page, see this picture here? This also means that we can use work to analyze roller coasters. And we are going to spend some time looking at roller coasters and amusement park rides. What takes more work? Lifting a 25 kilogram mass to a height of 4 meters or lifting a 50 kilogram mass to a height of 2 meters? What? Yeah. Twice as heavy, lifting it half as high is the same as lifting half as heavy, twice as high. You'll burn through the same amount of energy. You are doing work because you're lifting against gravity. I could crunch the numbers, but you know what? I think I can see it intuitively as well. Is that okay? I said to you way back here that the force must be constant. What if the force is changing? What if the force is changing? We can't use force times distance. This is where we need to bring in some calculus, but I can't give you the calculus equation. It involves an integral. I'm wearing one of my integral nerd shirts today. Work is also the area under a force versus distance or displacement graph. When do I use this? If they give me a graph and I notice that on the y-axis is force and on the x-axis is something in meters. Could be a d for displacement or distance, could be an x for position, meters. So, first of all, notice here we do have a changing force. It starts out constant, but then the force gets higher and higher and higher and higher. In fact, it ends up at 8 newtons, and it started out at 2 newtons. So is it a changing force? Yeah, okay. This question says, how much work was done in moving the object from 2 meters, draw a little line like that, to 5 meters, draw a little line like that? Well, the answer is that area. That area. For a candy, what shape is that? It has 2 parallel lines, 2 parallel sides, and 2 non-parallel sides. Okay? It's called a trapezoid. Called a trapezoid. Actually, for a real candy, does anybody know the formula for the area of a trapezoid? Every once in a while, I have a nerdy kid who actually does. There is one. Nope. And the reason is you've never been taught it. And the reason you've never been taught it is it's a shortcut, but it's unnecessary. See this trapezoid? Behold. I'm going to break it into a triangle and a rectangle. Yeah?
Is it A equals A plus B over 2 times A?
Where'd you find that? Where'd you find that?
Me?
Yeah. Did you Google it?
Yeah.
Sorry, no candy for you. But by the way, Mason, it is by the way. It's A equals, area equals, bracket, little a plus b close. You know what? The reason, first of all, it's a bit of a weird one to remember, but also it's redundant. Anytime you give me a trapezoid, I can break it into a rectangle and a triangle. And those ones you've been taught. Let's do the second one first, the rectangle. What is the area of a rectangle? How do you calculate it? This is going to be length times width, or some people say base times height. See that little rectangle? How long is it, Mason? Look at the numbers. How long is it?
4. No, wait. Why do you know what I'm looking at? You caught me.
How long is it? What number is this right here, Mason?
5.
What number is this right here, Mason?
2.
How long is it?
3.
Mason, how high is it?
2. 1.
Halfway to 4, which is?
2.
Mason, in your head, please, what's 3 times 2?
6.
So the bottom rectangle has an area of 6 joules. Let's find the area of the, shall we? Hannah, what shape is that first shape? Sesame Street is brought to you today by a 3-sided shape called a? So here's the question. What's the area of a triangle? Luke, this was the one that you rattled off earlier. I always write it as base times height divided by 2. But yeah, half times the base times the height, 0.5 times the base times the height. I'm good at dividing by 2, so I think of it that way. Do we want to go back to him? We should? Okay. Mason, my friend, here is the base of the triangle. How long is the base of the triangle?
Base is 3.
Good. Mason, my friend, this is the height of the triangle. What's the height? Don't say 8, because it's...
I was just going to say 6.
And then divided by 2. There's our triangle. Mason, in your head, what's 3 times 6 divided by 2? It's also the German word for no.
9.
What?
9.
No, yes. Okay. Jules. In your head then, Mason, what's the total amount of work moving this mystery? By the way, think about what we've just done. I don't even know the object. I don't know its mass. I don't know any, but I can tell you how much energy, how much work it took to move it from location 2 meters away to location 5 meters away. What do you get when you add these together in your head? 15 joules. I like this question. I like this question. There's going to be a energy graph, a force versus distance, find the work graph on your quiz and on your test for this unit. So if you give me a changing force, I just draw little dotted lines. I kind of shade in the area, Tyler, that helps you figure out. It's either going to be a rectangle, a triangle, or a trapezoid. And if it's a trapezoid, it's really a rectangle and a triangle. Okay? Now, if those of you that take calculus next year, one of the things you'll learn in calculus is how do I find the area under a curve like that? And there is a procedure for it. It's one of the reasons Isaac Newton invented the calculus. He wanted to find the slopes of curves, and he wanted to find areas under curves. And the area under a curve, it's called an integral, hence my integral shirt today. So now we have 2 definitions for work. The first one was the equation, force times distance. But this requires a blank force. What word did I say? I'm looking for a word that begins with the letter C. Constant. A second definition of work is it's the area under a F versus D graph. Under a newtons versus meters graph. By the way, remember I also said the units for work were Newton times meters, and when you find the area, you are actually multiplying y times x. You are actually going Newton times meters. Just saying. Okay. You're going to end up with 3 definitions for work. So when a question says how much work, you're going to go through a checklist. The first thing you're going to say is the force constant? Do I know the force? Do I know the distance? The second thing you're going to say is, oh, did they give me a graph? If not, you'll move on to the third definition, which we're not going to get to for a while. But it's the more flexible, more universal definition. Only Ethan's also way more work. No pun intended. Okay. How much work was done in moving this 10 meters? Is there a graph? Okay. What kind of a graph? What's on the y-axis? Force. What's on the x-axis? You know what? The work is going to be the area here. Also, I notice the force is changing. Do you see it's increasing? It's getting steeper. It starts out at 20 newtons. It finishes at 30 newtons. I cannot go force times distance. The classic mistake that I see, don't write this down, Hannah. The classic mistake I see kids go like this. Oh, the force is 30. The distance is 300. No. No. So, can I use force times distance? No. Did they give me a graph? Yeah. And they want me to move it 10 meters. I guess they want that area. It's also a trapezoid again. Well, wait a minute. Now it's a rectangle and a triangle. It's just that easy. I'll find the area of the first shape. I tend to just label numerals. Robbie, what is that first shape? Area for that. Oh, length times width. I can't remember if I put that on your formula sheet. I don't think I did. I think I might have figured that was fair game to ask you to by this time in grade 11 have picked up? Mason, what's the length of this rectangle? What's the width of this rectangle? Robbie, in your head? Yep. And then I have area 2. It's a triangle. What was the equation or the formula for the area of a triangle? Robbie, what's the base of that triangle? 10. What's the height of that triangle? Also 10. I guess it's 100 divided by 2. Total work? Yep. And also, it's a nice scalar. I can just add them up. I don't need to go fancy or anything like that. Okay. Work is force times distance. Work is the area under a force versus distance graph. Braden, work is really how much energy you transfer. Now, I'll answer your question. Stand up, seriously. I'm not going to have someone jump on your back. I just want you to imagine you're carrying someone. If you were walking straight ahead, you aren't doing any work on that person. That person has not gained or lost energy. But you asked, why do you get tired? You're resisting the force of, when you're carrying someone, which force are you? Okay, gravity. In which direction? So while you're standing, your muscles, big and small, all the muscles in your body that are involved in lifting that person are contracting and expanding a vertical distance, and they are applying a force over that vertical distance. That is where your body is burning energy, is doing work. That's why you're getting tired. So I fibbed a bit, but I can never resist putting somebody on someone else's back and having them do a piggyback all over the room, to get the illustration across that carrying something, you're not doing any work on the object. Yeah, you're going to get tired. That's because in your body, muscles are contracting, expanding, contracting, expanding, contracting, doing force times distance in the same direction as gravity. But here's the key. You haven't done any work on the object. You've burned some energy. Is that okay? Let's really fine-tune that. I think, is this the last one? Yeah, look at that. A box is being pushed along a floor, and it has a coefficient of friction, a mu, of 0.25. The person pushing applies a force of 525 newtons over a distance of 22 meters. You know what? I think I'm going to DULP. Who remembers what DULP stands for? I'm going to draw a little picture. Here's the box. What are the forces that are acting on this box? Get the obvious one. What else? Normal force. What else? We got the person pushing. That's the one we always called the applied, and I can even label it 525 newtons. Is there friction? How do you know? Hey, what's mu? What's mu with you? I'm going to assume friction is smaller. So okay, I'll put it there. All right. Got the visualization okay, Taylor? Taylor, what's the first thing asking me to find? How much what? Part A? Keep reading, keep reading. How much work is, keep going. Okay, how much work does the person do? The person is the applied force, and I think they're pushing it forward, so they are in the same direction, distance and force. The person does this much. The work done by the applied force, in this case the person, is going to be the applied force times the distance. It's going to be 525 times 22. The person used up 11,550 joules of energy. Not all of that, however, went into pushing this box. Some of that went into overcoming friction. How much work was done in overcoming friction? Well, the work done in overcoming friction is going to be the frictional force times the distance. Friction is what times what? Mu times the normal force. This is also good review. Times the distance. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? Okay? Because I didn't add any other vertical or up and down forces, right? I could. I probably won't in this unit. So it's going to be mu times m times g times d. So it's going to be, what's mu? I don't know. What's mu with you? 0.25. Mass, 124. G, 9.8. Don't need the negative. We're doing scalar here. The distance was 22. I get 6,683.6. I'll write the whole thing, even though I should round off because I just want to walk you through what's going on here. Is that right? 6683.6. 6683.6 joules. This here is energy lost. Lost to where? To be perfectly honest, the same thing, the reason you feel heat, you've actually heated up the floor. Now, as soon as you move past, the floor cools off very fast because the floor is massive and can absorb a lot of heat. But trust me, you've lost energy due to friction. You put in 11,550 joules of work, but not all of that went into the box. Much of that went into heating up the floor. This is lost energy. How much work, what's your net work that you did on the box? The net work is going to be the total minus what you lost. This is how much energy actually went into pushing the box. (4,866.4 joules. This part causes the box to speed up. That's the leftover unbalanced forcey part causing it to accelerate. That's how much energy there is going into making the box go faster. But most of your, in this case, most of the energy went into overcoming friction in the floor and heating up the floor. Okay. Is that all right? That right there is a pretty advanced topic. What's your homework? First of all, prepare for the test. But for Monday, number 1 is good. 2 is good. 3 is good. 4 is good. 5 is good. 6. So far I've assigned everything. Yeah, I know. We'll go with 7. 7 is tricky. 8 is good. 9 is good. I've assigned everything. I know. Oh, I have 2 number 9s. Huh, go figure. We'll do 9 and 9. Yeah, I assigned everything. It's not too bad. So number 9, the second number 9, which I'm going to change to number 10 right now because that irritates me. Anyways, here's a graph. So how much work is done by the force as it moves from 0.4 to 0.6 is going to be that area there. hey, it's a trapezoid, rectangle, triangle, etc. See if you can figure that out. Okay.